Hello everyone and welcome to Creature Archives. Today we're continuing the series Evolved Fiction. In this series I take iconic creatures from movies, myths, and games, and reimagine them through the lens of real-world evolution and biology, seeing just how close real life could get to turning fantasy into reality. In today's episode, we're bringing to life a creature with one of the most specialized and devastating natural weapons in all of Monster Hunter, Glavenus. This is no ordinary theropod. Glavenus wields a massive metallic tail blade that it can superheat and use to cut through flesh and bone quite literally like a hot knife through butter. Today we'll be exploring what evolutionary path could lead to not only a carnivorous creature with a natural blade for a tail, but one that can also superheat that tail to make it even more effective in combat. We'll break down all of this and more in this episode of Evolved Fiction. To bring Glavenus into the real world in a way that feels biologically grounded, while still preserving the traits that make Glavenus Glavenus, we first need to establish the core evolutionary goals this creature must meet. For our first goal, we want this final creature to be a carnivorous reptile with a primarily bipedal body plan, ensuring we create an animal that resembles Glavenus in lifestyle and overall build. Our second goal is the most obvious. The creature needs to have something akin to Glavenus' iconic tail blade. Additionally, this blade must be functional in combat, not just ornamental. And for our third, and maybe most difficult goal, this creature must be able to heat its tail blade to deal additional damage in combat without harming itself in the process. So, with our three goals established, it's time to dive into the evolutionary possibilities and see just how close nature could actually come to producing something like Glavenus. And if you enjoyed these scientific creature deep dives, don't forget to like the video and subscribe. There's plenty more on the way. Before we can build a realistic version of Glavenus, we need to figure out where its evolutionary story actually begins. To do that, we have to look across the major reptile lineages through history and ask the question, which group gives us the strongest foundation to eventually arrive at something that feels like Glavenus? So, the first place I looked was the most obvious one, the dinosaur group Theropoda. Quite simply, Glavenus looks like a theropod, it moves like a theropod, and its overall build is clearly inspired by dinosaurs like Tyrannosaurus rex and Carnotaurus. So, at first glance, it feels like we should definitely start here. Theropods already have a predatory lifestyle, the right skull shape, and are carnivores. But as perfect as all that sounds, there's one major problem. Theropods are absolutely not built for tail weapons. Their tails function as stiff counterbalancing rods, held straight out to stabilize the body and their massive heads. The muscles in a theropod's tail aren't arranged to swing or be used as a weapon. They're designed to keep the animal from falling forward. And on top of that, theropods are extremely front-heavy. Their entire body plan leans forward, and that center of gravity would make using a massive bladed tail very difficult. So, even though theropods match Glavenus stylistically, they simply can't take us down a believable path towards a fully functional sword-tailed predator. This meant I needed to look somewhere else, and when it comes to tail weapons, there was only one place to look: the dinosaur group Thyreophora. This is the armored dinosaur family, including dinosaurs like Stegosaurus, Ankylosaurus, and their relatives. These animals are the undisputed masters of weaponized tails. Stegosaurs wielded enormous stabbing spikes called thagomizers, and Ankylosaurs developed some of the most powerful bone clubs in history. If any real creature was ever going to evolve something even remotely similar to Glavenus' iconic tail blade, it would likely come from this side of the dinosaur family tree. But that still doesn't make the choice easy. Stegosaurs do have impressive weapons, but their overall build is tall-backed and bulky, and their tails are designed for spearing, not slashing. Ankylosaurs are even more extreme. They are generally low-slung tanks with heavy armor and devastating clubs, but generally they don't have blades. So the challenge became finding a species of one of these groups flexible enough to evolve in the direction we needed. And that's when the search narrowed down to two incredibly unique and unusual dinosaurs, Jakapil and Stegosaurus. Jakapil Kainukura is one of the strangest armored dinosaurs ever discovered. It's lightweight, much smaller than its relatives, and may have even been capable of standing or moving bipedally. That alone gets it closer to the general silhouette we want. It has armor, but it isn't buried underneath it, and its body plan is far more flexible than anything like an ankylosaur. The downside, it has no tail weapon, which brings us to Stegosaurus elengasen. Stegosaurus is a small late Cretaceous species from Chile with one of the most bizarre tail weapons ever discovered. Instead of spikes or a heavy club, it carries a flat, wide-bladed paddle, strikingly similar to the Aztec weapon Macuhuitl. It's the closest real animal we've ever found to something that even remotely resembles a tail sword. What makes Stegosaurus even more intriguing as a starting point is its overall build. It has less body armor than most ankylosaurs, and its limbs were more slender and lightly built compared to its relatives. This combination of reduced armor, lighter frame, and a unique bladed tail gives it a more adaptable starting point than the heavy tank-like ankylosaurs most people imagine. Over millions of years, those traits could create a believable evolutionary pathway towards a faster, more agile, and eventually more predatory descendant. So, when you compare these two options, Jakapil gives us the posture, but Stegoros gives us the weapon. And because the bladed tail is the single most defining feature of Glavenus, I have decided to start our evolutionary journey with Stegoros elengasen. Now that we've chosen our starting point, we can finally start following its evolutionary path forward, step by step from a small, unusual Cretaceous herbivore into a heat-wielding, sword-tailed super predator. And to get there, we need to begin at one of the most tragic moments in Earth's history, the KPG extinction. In real life, Stegoros went extinct with the rest of the non-avian dinosaurs, but in this scenario, a small, lightly built subspecies within the Stegoros lineage developed several key adaptations that allowed it to survive the impact, one of which would ultimately become the origin of the Glavenus lineage's defining trait. When the asteroid hit, ecosystems unraveled. Forest collapsed, global temperatures swung violently, and the food web disintegrated as plant life withered in the darkness. Large herbivores starved, and the predators that depended on them vanished soon after. But this surviving Stegoros subspecies already had advantages most armored dinosaurs lacked. It was smaller, more agile, less encumbered by heavy osteoderms, and flexible in both behavior and habitat use. Those traits alone improved its chances, but even those would not have been enough on their own. As resources disappeared, survival hinged on adaptability. And the Stegoros subspecies that pulled through were the individuals adapted to eat almost anything. In a world where plants were dying and competition for safe forage became brutal, natural selection favored omnivores. These dinosaurs scavenged carcasses, cracked open insect nests, and even hunted small vertebrates. Behavior that may seem surprising for an armored herbivore, but isn't actually that unrealistic. Modern herbivores such as deer, cows, tortoises, and iguanas are all well documented opportunistically eating meat when ecosystems are stressed or the opportunity presents itself. This dietary flexibility set off a cascade of evolutionary changes: slightly sharper teeth, stronger jaw muscles, quicker reflexes, and a more opportunistic predatory edge to their behavior. And as they shifted into a generalist lifestyle, something far stranger emerged: an adaptation that would eventually define the entire Glavenus lineage. During the ecological chaos after the impact, competition for carcasses and safe feeding spots became intense. It was during this period that a peculiar evolutionary quirk arose, reminiscent of the modern bombardier beetle, though arising from a completely different structure. Early descendants of Stegoros developed small dermal glands along the base and surface of their tail, embedded beneath and between certain osteoderms. These glands were originally simple scent-marking structures, but a mutation caused them to begin producing two chemically distinct secretions directly on the tail: a thin layer of sticky terpene-rich resin that was viscous, adhesive, and easily oxidized, and microscopic capsules containing a reactive oxidizing compound, functionally similar to the peroxide-based chemicals used by bombardier beetles. On their own, these substances remained stable and harmless. The tail was effectively coated with a ready but dormant chemical layer, which would only become active under the right mechanical conditions. When the tail struck or scraped against a hard surface, such as stone, armor, or dense wood, the friction and abrasion ruptured the oxidant capsules and ground the resin against the catalytic proteins embedded in the skin. This mechanical mixing triggered a rapid exothermic reaction: a brief searing burst of heat, a hiss of smoke, and a sizzling effect along the tail's edge. Not quite fire, but still a sudden scalding shock strong enough to burn flesh, irritate sensitive snouts, and send predators or scavengers running in surprise. And crucially, this wasn't only useful defensively. In a devastated world where carcasses were rare treasures, this brief but dramatic heat burst became a powerful deterrent. Small predators, scavengers, and competing omnivores quickly learned to avoid the smoking, sizzling tail of this strange little survivor. Individuals that produced hotter or more startling reactions held territory longer, defended carcasses more effectively, and drove off opportunistic thieves. In a starving world, this advantage was enormous. Over thousands of generations, what began as a mild friction-activated chemical quirk solidified into a stable adaptation, one that allowed this lineage to outlast the extinction when so many others perished. And it laid the biochemical foundation for the extreme weaponized heat systems their descendants would evolve millions of years later. Skipping forward into the Paleogene, as plant life slowly recovered and new ecosystems took shape, a dramatically different world emerged, one increasingly dominated by rising mammalian groups. This changing landscape pushed the surviving Stegoros descendants into more active hunting and scavenging roles, and over time, their bodies gradually adapted to match their increasingly predatory lifestyle. Their jaws grew stronger and their teeth reshaped, evolving from the simple leaf-shaped plates of their thyreophoran ancestors into serrated, slicing edges capable of processing both meat and tough plant matter, much like early carnivorous crocodilomorphs. Heavy ankylosaur-style armor became a liability for speed and agility, so the lineage retained only light osteoderms and back spikes along the back and hips, enough to provide some protection without impeding movement too much. At the same time, their hind limbs grew longer and more muscular, marking the beginnings of facultative bipedalism. These dinosaurs could sprint on their hind legs when pursuing prey, yet drop onto all fours for a stable low stance when wielding their tail as a weapon. This dual mode of locomotion allowed both agility and stability, giving them the best of both worlds as hunters and defenders. And through all these changes, the most dramatic transformation continued to take place in the tail. Over millions of years, the osteoderms in its tail gradually elongated and sharpened, shifting to become slightly offset to one side with a heavier backing, allowing the tail to deliver more powerful slicing strikes without bending or breaking. Keratin, the same material found in horns, claws, and bird beaks, coated the osteoderms through specialized follicular tissues, forming a dark volcanic glass-like layer that combined incredible toughness with a naturally honed cutting edge. As the lineage evolved, the tail blade became heavily mineralized to improve durability and heat resistance. Minerals such as apatite, magnetite, quartz, and trace silica were incorporated into both the keratin and the underlying bone, reinforcing the structure while allowing it to tolerate the rapidly increasing exothermic reactions triggered by the friction-activated chemical system. Over time, natural selection favored individuals whose chemical reactions produced stronger bursts of heat. The oxidants and catalytic proteins in the tail coating became more concentrated, and the mechanical design of the tail and groove system improved the efficiency of capsule rupturing and mixing, allowing localized temperatures to spike more rapidly with every strike. In addition to heat, the interaction of the mineralized surface with the chemical reaction produced a subtle glow along the cutting edge, a byproduct of exothermic energy passing through iron and silica-rich keratin. This luminous effect not only enhanced the intimidating display to rivals and predators, but also served as a practical signal to the Glavenus itself that the reaction had fully activated, ensuring precise timing for strikes during hunting or defense. This carefully tuned balance of asymmetry, reinforced backing, keratin coating, mineralization, and increasingly exothermic chemistry created a tail simultaneously lethal, heat-resistant, and highly reliable. Over time, the weaponized tail became the lineage's most defining trait, perfectly blending mechanical force with chemical firepower. As the lineage grew more predatory, the front beak underwent extensive mineralization, incorporating trace iron and calcium acquired from diet and environment. Along its inner edge, a specialized lateral groove developed, lined with micro-ridges of heavily mineralized keratin and embedded mineral flakes. These ridges served dual purposes. First, they acted as a sharpening and stropping surface, polishing the tail blade and maintaining a razor-like edge. Second, the groove became the controlled ignition zone for the tail's chemical system. When the tail was drawn through the mineralized groove, the abrasive ridges on the beak ruptured the microcapsules and ground the chemicals together. This mechanical mixing and catalytic contact triggered a rapid exothermic reaction, a brief searing burst of heat reaching up to 250 to 300 degrees Celsius, accompanied by smoke and a sizzling effect capable of singeing flesh and deterring scavengers. Over time, this friction-activated system allowed far more controlled, hotter, and predictable heating than the earlier activation methods, eventually producing the iconic heat activation of the Glavenus lineage. Introducing Caudopharum pyrobladius, the iron-tailed fireblade. This lightly armored, facultatively bipedal predator combines agility, precision, and a unique chemical-mechanical tail weapon. It stands roughly 2.8 meters tall at the hip and stretches 9 meters from snout to tail, weighing in around 1 to 2 metric tons. The jaws are powerful and serrated, capable of processing both tough plant material and flesh. Its hind limbs are long and muscular, allowing for sustained sprinting on 2 legs, while it can drop to all 4s for stability when wielding its tail as a weapon. The tail itself is an asymmetrical, heavily backed blade composed of fused osteoderms reinforced with keratin and minerals such as apatite, magnetite, and trace silica. When activated by friction in the mineralized beak groove, the tail's chemical system produces a rapid exothermic reaction, generating smoke, heat, and a subtle glow along the cutting edge. Caudopharum pyrobladius originated in central and southern Chile, and eventually expanded its range throughout much of South and Central America. Today, the species is recognized as having 2 distinct subspecies, a larger, now extinct form that once dominated Cenozoic landscapes as an apex predator, and a smaller modern subspecies that has persisted into the present day. Pyrobladius inhabited open woodlands, river valleys, temperate grasslands, and forest edges, environments that provided both cover for ambush and open space for sprinting attacks, allowing these predators to combine stealth, agility, and the unique utility of their tail blades in hunting. During the Cenozoic, the larger subspecies was a true megafauna hunter. Facultatively bipedal, it could sprint on powerful hind limbs to chase prey across open terrain, but often dropped onto all fours to stabilize itself while delivering precision strikes with its asymmetrical mineral-reinforced tail blade. This weapon allowed it to maintain distance from massive prey such as giant nodo-ungulates, toxodonts, proboscideans, and ground sloths. As megafauna populations decline, the large subspecies ultimately went extinct. However, the smaller subspecies, roughly the size of a wolf, survived by adapting to hunt smaller prey. This modern species, known as Caudopterum pyrobladius parvus, inhabit forest edges, river valleys, and open woodlands throughout South and Central America, particularly in areas with minimal human disturbance. They are versatile predators preying on deer, capybara, tapirs, and anything they can catch. Tail strikes are used to stun or injure prey, allowing for a clean killing bite. Reproduction is seasonal, timed with periods of resource abundance such as the rainy season. Females lay clutches of 3 to 6 eggs in concealed nests dug into soft soil or hidden among dense undergrowth. Hatchlings, like modern birds, are precocial, following adults within days of hatching, where they are protected until they are big enough to go off on their own. Outside of the breeding season, Pyrobladius is largely solitary, maintaining individual territories that it defends aggressively. Encounters between adults are rare and typically limited to brief confrontations over food, mates, or territory. Its survival into the modern era is a testament to the resilience of evolutionary specialization, demonstrating how a lineage once dependent on megafauna could adapt to a dramatically altered world. During the Cenozoic, the larger subspecies came into contact with early human populations migrating through South and Central America. Fossil and archaeological evidence suggests that these massive predators, capable of bringing down megafauna, indirectly competed with human groups for the same resources. Early hunter-gatherer bands likely viewed them with a mixture of fear, respect, and caution. Rock shelters from Patagonia to northern Colombia contain markings that many researchers interpret as stylized depictions of large tail-armed beasts with sweeping arcs trailing behind them, possibly representing the species' distinctive bladed tail. Among some Andean cultures, these creatures appear in myth as boundary spirits, guardians of the land who punish those who trespass into forbidden hunting grounds. In parts of southern Chile, stories describe them as omens of conflict or famine, appearing only in the years when prey animals were scarce. By the time European colonists reached the Americas, the megafauna hunting giants had already vanished, casualties of ecological collapse and the disappearance of their primary prey. Only the smaller subspecies, Pyrobladius parvus, remained. While Pyrobladius parvus generally avoided large settlements, in remote regions, colonists and explorers occasionally reported tense and dangerous encounters. A Pyrobladius stepping onto a trail ahead of a travel party, raising its armored tail, and rattling its keratin plates in warning. Interestingly, the range of Pyrobladius parvus overlaps with another remarkable survivor of the KPG extinction, Noctivorax rubriferum. While Pyrobladius favors more open terrain, the two predators share forest edges and riverine corridors, creating zones of interaction and rivalry. Some researchers speculate that the evolution of Pyrobladius's exothermic chemical adaptation may have been shaped in part by the presence of Noctivorax, exploiting the latter's vulnerability to heat due to its flammable, oil-rich skin. Whereas Noctivorax is a strictly nocturnal, stealth-oriented hunter and is rarely even seen by the indigenous people who live alongside it, Pyrobladius parvus is bold and unmistakable. Active during daylight and dusk, flashing bright tail coloration during threat displays, and far less concerned with concealment, it became widely known far earlier. Its striking appearance and confrontational displays made it a prominent figure in indigenous oral traditions and one of the first non-avian dinosaur species documented by colonial observers. Today, Pyrobladius parvus survives as a living relic of its once widespread lineage. Its remaining populations are fragmented and scattered across Central and South America. Ongoing habitat loss, driven by agriculture, deforestation, and expanding urban development, remains the greatest threat to its continued existence. Due to its rarity and declining population numbers, Pyrobladius parvus is currently listed as endangered on the IUCN Red List. Conservationists stress the need to preserve large connected tracts of native habitat and to maintain ecological corridors to prevent genetic isolation. Modern research tools are finally illuminating aspects of this predator's life that were once based only on local stories and occasional encounters. Remote camera traps have documented tail strike behaviors in unprecedented detail, while field studies are beginning to map its diet, movement patterns, and interactions with other predators and prey. Its continued survival tells a story of resilience, adaptability, and the enduring presence of one of the world's most unusual and formidable predators. Thank you everyone for watching. If you enjoyed the video, don't forget to like and subscribe so you won't miss any future content. And if you want to further support the channel, consider becoming a YouTube member today. Not only will you help support me in making the best quality content I can, but you'll also gain early access to videos, sneak peeks at upcoming videos, access to the members-only section of the Creature Archives Discord, and a special thanks to all my current members. Your support means the world and keeps the channel going. Until next time, stay curious, and I'll see you all in the next video.